Hi, I'm Chris Hanusa. I'm a mathematician at Queens College of the City University of New York. I'm going to be talking about data mining imaginary maps, where this is a collaboration with Emily Garfield, who's an artist in New York City. She makes amazing cellular artwork that we're going to be analyzing and investigating. Hello, everybody. So my name is Chris Hanusa. I am at Queens College of the City University of New York, and I'm going to be talking to you about a project that I did as a collaboration with an artist, Emily Garfield, who's in New York City. So let's do with what we have. Okay, so let me share with you. Let me show you a picture of something amazing that Emily draws. So she makes these amazing map-like objects where they are built using an algorithm in her head. You would have seen a picture of her watercolors. These are watercolor-made objects. She first draws the regions and then fills them in. She draws the regions algorithmically with the algorithm in her head, and then fills them in with the colors that she feels like they should be there. Right? This is a purely artistic method of creating beautiful, beautiful works of art. So one of the things that we'd like to know is so Emily came to me and said, hey, this is an interesting thing she was always interested in learning more about her work. So questions that came up to her, so these maps that she makes, they are not actual places. It's not like there's a place that she's thinking about when she's drawing these, but the question is, well, what makes them look like maps? Everybody sees that and says, that looks like a map. And then if you have this map, what would life be like if you were there? If you were living in that block, what would life be like there? Another thing is that she was really interested about, there's the work of Jackson Pollock. There's been academic work trying to learn about the fractal nature of his prints, and there's various, so is there some fractal nature of Emily's work? There's also amazing data visualization of cities here. What you would see here is you would see a map of New York, and then a map of New York sorted by blocks. So block size, block shape, and then laid out in a beautiful visualization. Similarly, Jeff Boeing's work takes a map of a city and then figures out the orientations of the edges based on the directions and the orientations of the roads. Okay, so the motivation is, what can we learn about the questions? So these are the questions I wanted to ask. Can we quantify Emily's maps? Can we learn things about the maps? Can we learn things about the color palette that she uses in her pictures? What can we learn about the structure of the blocks and of the roads? Can we analyze the neighbors of blocks? What type of fractal qualities are there? And can we come up with an algorithm to create maps that look like Emily's maps? And so the overarching question is, well, what really makes a map a map? That's our investigation. Okay, so this is also a huge file. It's 250 megabytes. So that may be paying into this too. So here's a black and white version of a map. Hopefully later on we'll see what the map looks like. But I needed to take this colorful map and import it into Mathematica. So how do I do that? First I tried, so what I wanted to do is take each of the cells and understand each of the cells individually. So in order to do that, I needed to make a black and white version of this map. So I wanted to do that algorithmically. I tried a number of different things, binarize. I've also used morphological binarize. But whatever I did, it was never perfect. So I needed to get Emily to come in and do some manual cleaning of the final version that I had. once you get a final version of it, then you can use image mesh to take it out and get each of the blocks that are in the picture. And then we can take the components, and then this would be one of the blocks that we're going to look at. And then from that, we can use a mask and get a mask of each of the pieces. So these are what each of the individual pieces would look like of this. And then what we can do is we can average so one of the things is that this mask, on a really large picture, the mask doesn't, you need a smaller mask for it to actually process in a reasonable amount of time. So I made a smaller rectangle of each of the sizes of the blocks, and then I averaged over the non-white parts of this rectangle, and you can see that I can extract the color from each of the blocks. So once you do that, look, a map. Okay, so this is one of Emily's pictures. And then this is what Mathematica will see after I've done the transformation, which has taken each of these blocks and given them the right size and the right shape. And now they have the average color of each of the regions. So that I can do for almost any map. Any picture that she gives, I can do that. But if I'd like to learn more about the road network, that is intensive in many, many, many different ways. It's computationally intensive. It's also human labor intensive. So I used skeleton transform, pruning, thinning, and binarizing so that I took this map where there are roads of a certain width and made them now one pixel wide roads. And then you can still see, maybe you can see, maybe you can't, there's little artifacts on here that have to be gotten rid of. So we found that the best way to do that is just to do some more manual cleaning. You have to also get rid of all the little artifacts that are on the edges. And then you can apply morphological graph, and then you get a graph. Okay, but again, this graph isn't perfect because there's little junctions, there's little vertices on these edges. There's also, like, maybe there's multiple vertices that really should just be one vertex corresponding to a neighborhood. So I had to do some manual cleaning of that. I had to coalesce vertices. I had to remove the non-connected parts, remove the degree 2 vertices, and then in the end, every vertex has degree 1 or 3. I then added some corner vertices to make the boundary faces, and did some more final manual cleaning. And then that gives us the structure of the road network. And then if we want the structure of the block network, we need the dual graph. And so we find the dual graph of the graph, and we need to put it where the vertices are on each of the face centroids. And so after dealing with that, you now have both the road network and you have the block network. And so you now have two different things. You have the components, and you have the centroids of the components, and then you have the block network where you had vertices that came from the faces. And so you had to then align the two, and then after all that, you finally get a picture where you have every component, you have it numbered, and you know exactly which vertex it is in the graph, and then you can do some analysis. So that's a lot of stuff just to get it into a right format, and there was a lot of manual parts, so really you can't do the biggest maps that she has, you can't analyze those, but the smaller ones you can analyze. All right, so the first thing I want to talk about is color analysis. So often people think about RGB, how much red, how much blue, how much green there is in a color. I liked thinking about it more in terms of LCH, so lightness, chroma, and hue. So you have some amount of how bright it is or how saturated it is and what hue the color is. So for each of the maps, you can create one-dimensional plots of the color distribution. So of that green map, you have, this is the distribution of the colors in terms of lightness, in terms of chroma, in terms of hue. But it gets more interesting when you put the dimensions together. So here is a picture where I've taken each of the regions, each of the blocks, and then laid it out in terms of chroma and hue, so that you get more, you can see a little bit more of the structure of the color field. Here's hue versus lightness, and here's lightness versus chroma. But really the best thing to do is to go into one more dimension, which is to look in terms of, these are all of the different blocks and all the different colors. You can see the distribution of the colors from the map based, and each of the circles represents the area of it. So you get an idea about the structure of the color distribution in the map. So here I'm going to show you 3 more of them. Well, I'm going to show you 3 more color distributions without the maps. But you can see here's this was, you can imagine it's mostly a red map, right? Whereas here's 2 other ones. These are more colored maps with many variety of colors. But what I hope you can see here is there's a structure to the colors that are used, right? I sort of feel like there's a mountain, right? For each of the dominant colors, there seems to be like a mountain of the colors that are in the blocks, right? And I feel like what that means is that if you want a fingerprint of Emily's color schemes, then you have this mountain quality to the colors that are present in the pictures. All right, so since I'm here, here's a picture of Emily. This is what Emily looks like. And so here, okay, here we go. So here's a picture of this map, and here's the 3D version of that map. And then here's another one of these pictures, and these are the 2-dimensional and then 3-dimensional versions of the color schemes. So let's go into some of the other types of analysis that you can do. So we can also look at the blocks individually. We can ask the question about the size of the blocks. We can ask a question about the density of a block. So if we take a block and we do 3 times the size, how much of that area is taken up by other blocks? We can talk about how rectangular a block is. And so let's say you wanted to look at the block size. So here are 6 different pictures. And for the 6 different pictures, this is a histogram of the sizes of the blocks that there are. So if you take the log, instead of looking at the size, but you look at the log of the size, you can actually see a pretty striking similarity in terms of the block sizes that appear in the maps. They seem pretty normal. So I thought that was an interesting takeaway from the setup. One thing I'm pretty proud of is that you can see the color schemes of these maps. These are extracted from the maps themselves by clustering the colors, and then based on the cluster, and you cluster in terms of a certain number of things, and based on those colors, you then extract the average color for that cluster, and you assign it a weight based on the area of the map that's covered by that cluster. And then this is basically, here are the main colors that appear in the picture, sorted by the area that they cover in the map. All right, let me skip a couple of those. We can also talk about the road analysis. So we can talk about the width of the roads. We can talk about the length of the roads, the distance between the intersections. And we can talk about the orientation. So this work by Jeff Boeing had pictures of cities, and then the classic, basically a circular histogram of the density of the direction of the roads, and I was able to replicate that in Mathematica. And so what do? You take you can see in this map, most of the roads that go this direction are kind of bending downwards, which you can see also in this histogram. This histogram represents the street orientations. So it's saying most of the roads go this way. There's a good chunk that goes this way, but there's not many roads that go this way or this way. What's that? Right. It should, so if it's a square grid, right? If it's a square, so So I'll be back in a second. But here, this picture is much more bubbly. And in this, there's not really a direction that's more there than others. And so you can see that the histogram is basically a circle because the directions of the roads are rather uniformly distributed. So here's four different of these visualizations. Here's one more. So in terms of the real world, normally especially in the United States, roads are put on grids. So here's a picture of a commission that Emily did in about a town in Massachusetts. And there you can really start to see the grid nature, and that's shown in the visualization because most roads lie on those perpendicular axes. All right, so we can ask things about the number of neighbors, the neighbor size ratio, so how different are two blocks that are neighbors, how different are the colors. I'm going to skip those because I think people are more interested maybe in terms of fractal analysis. So if we wanted to talk about what would it mean for one of Emily's maps to be fractal? Well, I think the best way to think about it is that the sub-images would look a lot like the big images. So the neighborhoods around small blocks, do they look like neighborhoods around large blocks? And so in order to do that, we can compute the quintiles of the block sizes. So we can break down the blocks into being the smaller blocks, the medium blocks, and the largest blocks, and see if we can compare those sets and see if the pictures behave similarly for the small ones, the medium ones, and the large ones. And so, for example, if we wanted to look at the color distributions, so quintile 1, the smallest, the medium, and the largest, if I look at this just like from far away, they all kind of look the same. I mean, there's a little bit of difference maybe in this picture and maybe a little bit here. But in general, it feels like the colors don't actually depend on the block size. So that's one thing that's independent. One thing that's dependent is that the larger the block is, the more neighboring blocks there are. That's to be expected. If you have a large block, there's more things around it. And the larger the block, the wider the road is. So given a block that's a larger block, you have a larger road surrounding it. Although it didn't actually behave exactly the way I thought it would behave. So let's talk about creating a new map. So I used Mathematica to generate some new imaginary maps. And so in order to do that, I generated random block positions. I found some block boundaries. And so I used Voronoi and Delaunay triangulations. And then I did a double dual. So I used a dual graph and another dual graph. And I know that's going to give you back the same thing. But what I really did is I changed the position so that it had a nicer layout. And so I did it twice. And what I get is I get this region, which starts to look a little bit blocky, right? Different sizes. I then took these polygons and I rounded each of the polygons. I added a little bit of space in between them. And then I colored them using the distribution of colors that I found from, we learned about earlier, which is that there's going to be some major colors, and we'll sample colors from a distribution that has a nice mountainous feel to them, and we'll prioritize colors based on proximity. So all of the grayish ones are over here, and then the purplish ones are here. And when I do that a couple of times, I came up with some pieces of art. So if I chose vertices deliberately, you get this type of some interesting graph structures. If I chose random vertices, I get this more nature, organic feel to them. And so what are the takeaways from our project? Well, I would say that yes, we can quantify her maps. There are certain defining characteristics that there are in the maps. I wouldn't say that they're fractal. It's a little disappointing, to her and me. But I think it was interesting to try to come up with some of these metrics that we could investigate. I'm not just a mathematician, I am also a mathematical artist, so it's a lot of fun to make these new maps. Choosing points is a hard thing to do, or choosing where you want your blocks, and I love generative art. So Emily's takeaways were that it was really fascinating to see a statistical analysis of her artwork. It makes her think about her art a little bit differently, which, if you go into, is that going to change the way she makes art in the future? Well, she'll probably be informed a little bit by what we were talking about. The art was more random than she expected. She was going in and thinking, I'm doing this very algorithmically. But when you look at some of these things, there's more randomness than she expected in terms of the process, and then the paper, and then the humidity, and then all the tools that she was using. And a philosophical question is, when you do this with a piece of art and you learn about it from a quantitative point of view, are you really taking the art out of the art, right? Is this now super numerical and is not artistic? Or is this just a different layer? Or what's happening there? So this is a philosophical question. There's lots of things that we'd like to learn more about. But what I can say is, if you're interested in seeing these slides, as you saw, you can go to my website and download these slides. And if you're interested in seeing me as an artist, I have my art portfolio here. You can follow me online. I have a mathematical jewelry business that I've created using Mathematica. And I will be having a lunch roundtable for people interested in talking about art and jewelry at lunch tomorrow. This is Emily's information, and I'll do one final shout out to the SciArt Initiative, which is a group of people who are interested in both science and art and the spectrum in between those two. And that's where Emily and I met, and it's a really nice community. So thank you very much.